Hi, welcome to Algebra 2 Common Core. Today for our lesson you're going to need your graphing calculator as well as several different color pens. So pause the video and go find those things if you don't have them with you right now. Now the last kind of transformation that we're going to take a look at is stretching and compressing trig functions horizontally. So we want to be able to do this so that when we model with real-world problems, we don't always have to have a period of 2 pi. So on this graph, we are looking at the graph of y equals 3 cosine of x. I want you to stop your calculator, stop the video for a minute and plot this on your graphing calculator. Now we are actually going to do the graph of y equals 3 cosine of 2x. So there's a couple settings that you have to make sure of. First of all, make sure that your calculator is set in radian mode. Make sure that you have a window on your graph going from negative 2 pi to 2 pi on the x-axis. And you'll notice that we are counting by pi over 2. So set that in your window. For my y's, I would like to go from negative 4 to positive 4 and count by ones. And then enter in your y equals 3 cosine of 2x. So what we're going to do is then draw the graph that we see on our calculator right on this same grid. Now when I took a look at my graph, I'm going to start with the y-axis. I'm going to change color here. And on the y-axis, I see that I reach right here at 3 when x is equal to 0. And as I go across halfway between 0 and pi over 2, which of course would be pi over 4, I hit 0. At pi over 2, I should be at negative 3. Then I go back to 0 halfway between pi over 2 and pi. And then I go back up to 3 at pi. So you'll notice that I've squeezed this graph horizontally. I've made it smaller. This is a compression. So I'm fitting 2 graphs within the same amount of region where I normally see just one cosine function. So go ahead and plot these points on your piece of paper and continue the pattern as we go along. So from that point up at 3, I'm going to go back to 0, then back to negative 3, and to 0, and back up to positive 3. So when I connect these points, I should see my complete cosine curve happening right there, and then another complete cosine curve happening right here. So I see within that 2 pi region right here, I'm actually seeing 2 complete cosine curves. Now go the other way. I'm going to pause the video for a minute and you pause it as well. And go ahead and fill out the left-hand side. Replicate what we did on the right side. So compare your graph to mine, and we should see 2 complete cosine graphs to the left of the y-axis and 2 complete cosine graphs to the right of the y-axis. Remember that our cosine pattern goes start at 1, go to 0, then negative 1, then 0, and then back to 1. So if this one has an amplitude of 3, then I'm starting at 3, going to 0, going to negative 3, back to 0, and up to 3 again. So how many complete cycles do I have within 2 pi radians? That means that I'm only looking from 0 to 2 pi to count my cycles. And I see that there are 2 complete cycles of the cosine curve, 2 full patterns. Now I'm going to go with a new function here, y equals 3 cosine of 1/2 x. So again, I want to switch colors and I want to type this into my graphing calculator so that I can see the effect of putting a 1/2 in front of the x instead of a 2. So pause the video while you put that on your calculator and see if you can go ahead and graph this on the axes and then come back and check with mine. So taking a look at the red graph that I've drawn, I'm going to label the red one y equals 3 cosine of 1/2 x. And you should see that I began at, again, the y-axis with a height of 3. This one is a horizontal stretch, so that means that it took me all the way to go over to pi to have an answer of 0, and then at 2 pi, that's where my answer was -3. Now, continuing the graph on the left side, I've got to follow the pattern and say, here's my 0 at -pi, here's my -3 at -2 pi. So what happens with this one is when I am looking just from 0 to 2 pi, I'm only seeing half of a cosine curve. I'm only seeing the part that I like to call the going down the roller coaster, starting at the top of the hill and reaching the valley. So I only see 1/2 of a cycle in the red graph. And again, I'm just looking at a 2 pi width. So let's go ahead and look at some definitions that are going to be important in this lesson. Frequency is the number of complete curves that I have in 2 pi. So it was important that we were able to take a look at just a portion of the graph that we have drawn and see how many complete cycles we see. We are going to use the capital letter B to stand for frequency. And you'll notice that we find the B in the equation in front of the x. It's the coefficient of the x. So that's telling us how many complete curves we have. So if you look at the graph above, the two that we drew, the first one that I drew in blue had a 2 in front of the x, and that corresponded with having 2 complete cosine cycles in 0 to 2 pi. And in the second graph that I drew, the red one, I only had 1/2 of a cycle, and that's because my equation had a 1/2 in front of the x. Now, the other term that we're going to find very important in this lesson is period. The period is the width of one complete cycle. We're going to use the capital letter P to stand for period, and we are going to find that the period is just equal to 2 pi, which of course is my width, divided by the frequency, which is the number of complete curves. And that tells me how much it's going to take to make one complete width. So based on that information, let's move on to example number 2. Example number 2 says, consider the graphs from example number 1, so the ones that we've already drawn above. So the first one, A, is the one that was given to us in black ink. So the frequency for this one, the B value is going to be equal to 1. We had one complete curve from 0 to 2 pi. The period is going to be the width of that one curve. It took us 2 pi to make one complete cycle. So we'll call the period 2 pi. For the second graph that we drew, the one that was in blue, the frequency is 2, and again that also corresponds to the coefficient of x, but the period turned out to be just pi. So I was able to fit one complete cosine curve between 0 and pi. Every single interval that was pi wide, I could fit in one complete cosine curve. For the last graph that we drew, the red one, the frequency was 1/2. That corresponds to the 1/2 in front of the x in the equation, and I could also see it on my graph because I could only see half of a cosine curve between 0 and 2 pi. Now, we can't see this whole thing, but in 2 pi, I only got half of a graph. So if in 2 pi I only got half of a graph, that tells me it's going to take 4 pi in order to get one whole graph. So the period for this one is going to be equal to 4 pi. Now, in example number 3, we're going to see how these results then tell us how the period and the frequency are related to each other. So if I take a look at the examples that we just filled in, I know you're going to be flipping back and forth between page 15 and page 16, but you'll notice that for the black graph, when I multiply B times P, I have 1 times 2 pi, and that gives me an answer of 2 pi. Now watch what happens as we go along to the other two examples. If I multiply B times P, I had a frequency of 2, and I'm multiplying by pi, so that also gives me 2 pi. And for the red example, when I take 1/2 and I multiply it by 4 pi, I still get exactly the same answer, 2 pi. So what I should notice here is when I take the product of period and frequency, I am actually always going to get 2 pi. So this should be something that's constant for our trig functions, especially sine and cosine. So p times b is equal to 2 pi. What that's telling us is the product of the period and the frequency equals 2 pi. Now also notice how the p and the b are related. What we should see is that p and b have an inverse relationship. What that means is that as one goes up, the other one goes down. So we could write that as the b value, the frequency goes up, the period goes down. Now, of course, this inverse relationship would go the other direction also. As b goes down, p would go up. So in example number 4, we're going to use this information that p times b is equal to 2 pi. And we want to find the period of each of the following. So again, the period means we're looking for the p. In all cases, we know that p times b is equal to 2 pi. So for our first equation, I've got y is equal to 6 sine of 4x. So the first thing that we're going to do is take a look at the coefficient of the x. I know then that that tells me that the frequency, the b, is equal to 4. So the question is, what does p have to equal? I want to solve for p such that p times 4 gives me 2 pi. Dividing both sides by 4, I get that p is equal to 2 pi divided by 4. So therefore, the period for this one is going to be pi over 2. Let's look at the second example. Look at our coefficient of x. That's going to tell me my frequency. So the frequency in this case is pi over 3. If I want to solve for the period, then I'm going to say the period times pi over 3 has to equal our constant product of 2 pi. Now in this case, I want to get the p by itself, so the best way to do that is to multiply by the reciprocal of pi over 3. So I'm going to multiply the left side by the reciprocal, 3 over pi, and I'm going to multiply the right side by the reciprocal, 3 over pi as well. So you'll see that on the right side, the pi's cancel, and I get an answer of 6. On the left side, both the pi's cancel and the 3's cancel, telling me that the period for this one is equal to 6. Let's finish it off with example C. So I'm going to look for my coefficient of x, and that's going to tell me that b is equal to 2/3. So that's the frequency. P times 2/3 has to equal 2 pi. So just like the previous example, I want to multiply by the reciprocal of 2/3, in this case 3 over 2, on both sides of the equation. So when I do that, I'm getting P is equal to, cross cancel the 2's, so I have a final answer of 3 pi. So I hope you're noticing that sometimes I'm ending up with a period that has a pi in it. Other times I'm ending up with a period that doesn't have a pi in it. It's all dependent on whether my frequency has a pi. So don't be alarmed if sometimes you have pi and sometimes you don't in your answer for the period. The period is just telling us the width of the graph. Sometimes it's going to be helpful for us to have a width that's 6 versus a width of 3 pi. We're going to see a lot of examples coming up in the next few lessons where we're going to be changing the period and seeing how it affects our graph. So now we're going to move on to example number 5 where we've got a graph to sketch. What I'd like you to do is again get your graphing calculator And what we need to do is find the length of one full period for this graph. Now for this example, we have not been given our grid with units on our axes. The x-axis especially, we need to be able to label. So we're going to use the information about frequency and period in order to figure out what our labels are going to be on our axes. So let's start with our coefficient of x, and that tells us that the frequency is equal to 4. Now again, remember what that means. If I had 2 pi, if I had a graph that was from 0 to 2 pi, I would have 4 complete cycles in that region. I only want to graph 1 cycle, 1 full period. So what am I going to do? I'm going to say that the period times the b value must equal 2 pi. I think we've seen this one before, so if we divide both sides by 4, we're getting 2 pi over 4, which is just pi over 2 for the period. Now what that means is, on my graph, I want to start here with 0, but then I want my width to go all the way over 2 pi over 2. Now I've got to divide up my axes. So halfway to pi over 2, half of pi over 2 is pi over 4. What I'm really doing is counting on the x-axis, so I have to figure out what's half of pi over 4 now, and that's going to be pi over 8. And again, in each case, all I'm doing is saying half of the interval that I currently have. And that's where I got the pi over 8. So really what we're doing here is counting by pi over 8. There's 1 pi over 8, 2 pi over 8, so the next one's going to be 3 pi over 8. And then the last one would of course be 4 pi over 8, which is pi over 2. Now go in the negative direction, so same exact labels. Negative pi over 8, negative pi over 4, negative 3 pi over 8, and negative pi over 2. Okay, the next thing we want to recognize is that our amplitude, or our height on our graph from the midline, is going to be 2. So when I'm making my sine curve, the height of the peak and how low the valley goes is going to be 2 and negative 2. Remember that my sine curve begins at the origin, so I'm going to put my first point right there at the origin. And then follow the pattern for the 4 values coming after 0. So I know that sine should go from 0 to its height. Well, this one's height is going to be 2 because the amplitude is 2. Then back to 0, then to negative 2, and then back to 0 again. Follow that pattern going to the left. So I see that my points should look something like this. And I'm going to go ahead and connect those values. Oop, I slightly missed that bottom, but my curve looks pretty good. So I see that this is going to be the graph of 2 sine of 4x. Again, remembering that I adjusted the way that I labeled my x-axis. So for our last 2 examples, we have some real-world application problems. Exercise number 6 says the heights of the tides can be described using a sinusoidal model of the form y equals a cosine of bx plus c. You'll see that sometimes we use sine and sometimes we use cosine to model trig application problems. If high tides are separated by 24 hours, which of the following gives the frequency b of the curve? So this information about taking 24 hours to make one complete curve actually tells me the information about the period. So the period means I need 24 hours to make a complete cycle. Again, remembering that P times B has to equal 2 pi. Let's plug in 24 for P, and then let's solve for the B. So we're going to divide both sides by 24, so B is going to be equal to 2 pi divided by 24. And that can be reduced, of course, by canceling the 2 with the 24. So I get an answer of B equaling pi over 12. and again, that represents the frequency. So this time, the frequency had a pi in it, while the period did not. Again, the 24, it was important to recognize that the 24 stood for the number of hours, so it was a time quantity. In example number 7, it says the voltage used by most households can be modeled by, this time we're using a sine function. So it says the maximum voltage is 120 volts. So that maximum voltage is actually giving us our amplitude on our curve. So we're going to say, okay, I've got to have 120 in front of my sine function. And I see that all the choices do have that. Now, here's the important piece of information. There are 60 cycles every second. So if there are 60 cycles each second, what I need to know is how wide is one cycle. So to do that, I'm going to say, well, to take one cycle, we're going to have to divide by 60. So that means that one cycle is going to take 1/60th of a second. Now the width of each cycle is just the period, so I know that P must be equal to 1/60. We want to use our equation P times B equals 2 pi so that I can put the B into the equation. You'll notice that, again, the B is the coefficient of the x, and I need to know what goes in front of the x. In this case, it's the variable t instead of x. P is 1/60th. I want to solve for B, and the product has to equal 2 pi. So if I multiply both sides of the equation by 60, then that's going to tell me that B has to equal 120 pi. So I am getting a coefficient of x of 120, coefficient of t of 120 pi. You'll notice that the only one that has 120 pi in front of the variable is choice 4. So that's going to be our trig equation showing an amplitude of 120 and a frequency of 120 pi. Thanks very much for working on frequency and period tonight. We'll work some more in class on these applications and graphing problems so that we can get a better feel for frequency and period of trig functions. Have a good night. We'll see you next time.